Ever notice how stars twinkle? That same twinkling is what blurs out telescopes too, and astronomers call it seeing. When light from a distant star enters Earth's atmosphere, it passes through layers of air moving at different temperatures and speeds. Each one of those layers bends light slightly, but enough to distort its path. To your eye, it makes the star flicker, but through a telescope it's worse. The image jitters and blurs, destroying sharpness. The bigger the telescope, the more atmosphere it has to look through. So the worse the effect becomes. That's why even massive ground-based telescopes used to struggle to see as clearly as tiny ones in space. Early observatories were built on mountaintops to get above as much turbulent air as possible. Sites like Mauna Kea in Hawaii or Cerro Paranal in Chile were chosen for their calm, dry air and stable temperatures, ideal for steady seeing. And even then, the atmosphere's distortion remained a stubborn problem. Engineers tried long exposures, stacking images, or computer corrections, but the stars still wobbled. It wasn't until the late 20th century that we found a real solution, or rather two. In 1990, NASA launched the Hubble Space Telescope, above the atmosphere where seeing does not exist. Without turbulence to blur the view, Hubble revealed sharp, crystal clear images that changed astronomy forever. But space telescopes are limited. They're expensive, hard to maintain, and small compared to what we can build on Earth. So the next challenge was clear. Could we somehow give giant ground-based telescopes Hubble-level clarity without ever leaving Earth? That's adaptive optics. The system uses a reference star, or a laser beam projected into the sky, to measure how the atmosphere distorts light. Then, tiny actuators on a flexible mirror bend it in the opposite way, canceling out those distortions almost instantly. This happens hundreds or even thousands of times per second, sharpening the image so much that a 10-meter telescope on Earth can see as clearly as Hubble in space. It's one of the greatest breakthroughs in modern astronomy. Observatories like Keck, the Very Large Telescope, Gemini, and Subaru all use it to study exoplanets, nebulae, and distant galaxies with stunning clarity. In ideal conditions, these systems can rival or even surpass Hubble's resolution. But getting there isn't easy. Adaptive optics takes enormous effort. Powerful lasers, ultra-fast computers, and mirrors that flex thousands of times per second. And even then, matching Hubble's consistent clarity requires huge, expensive telescopes and perfectly steady air. The payoff, though, is freedom. Unlike space telescopes, ground-based ones can be upgraded, repaired, and constantly pushed further. That's why the new giants like the Giant Magellan or the 30-meter telescope are being built with adaptive optics at their core, turning Earth's atmosphere from an obstacle to an opportunity.